Welcome back, tech enthusiasts. It's always a delight to have our seasoned followers around, and if you're new here, you're in for a treat. Today, we're peeling back the layers of mystery surrounding robotics. We're taking a simple, step-by-step journey through the process of creating a robot. So if you haven't done so already, hit that subscribe button and activate the bell so you don't miss out on future updates. Are you ready to dive into the world of robotics? Here we go. Firstly, what is a robot? Well, a robot can be defined as a machine capable of carrying out a series of actions automatically, especially one programmable by a computer. These actions can range from simple tasks like picking up objects to more complex ones like performing surgical operations. Robots come in various shapes and sizes, each designed for a specific purpose. For instance, industrial robots are used in manufacturing to automate tasks that are dangerous, repetitive, or require precision. On the other hand, we have service robots that assist humans in tasks such as cleaning, delivery, or even companionship. Then there are exploratory robots, used in fields such as space exploration and underwater research, where the environment is too harsh or hazardous for humans. These robots can withstand extreme conditions and send valuable data back to us. So robots are essentially our tools, our helpers, and sometimes our explorers. With a basic understanding of robots, let's move on to how we can build one. To start building a robot, you first need to gather all the materials. Let me walk you through what you'll need. First up is the brain of our robot, also known as the microcontroller. This is essentially a small computer that will control all of our robot's movements. Next, we need motors. These are what will physically move the robot, turning our electrical signals into actual movement. Third on our list are sensors. These act as the robot's eyes and ears, allowing it to interact with the world around it. Last but not least, we need a power source. This could be a battery or a power adapter depending on your preference and the robot's needs. So, to recap, we have the microcontroller, motors, sensors, and a power source. These are the key pieces that will bring our robot to life. With all the materials in place, we're ready to start assembling our robot. Now the exciting part begins, assembling the robot. This is where we take our components and begin to build our mechanical marvel. The first step is to connect the motors and sensors to the microcontroller. This might sound complicated, but it's actually quite straightforward. The motors are what will allow our robot to move, while the sensors are its eyes and ears, helping it interact with the world. To attach the motors, we'll need to identify the correct ports on the microcontroller. These are usually labeled, making it easy to match each motor to its corresponding port. Once they're connected, we'll secure them in place with some screws. Be sure not to over-tighten them, as this can damage the motors. Next up are the sensors. These vary depending on the type of robot you're building. Some robots might have light sensors to detect changes in brightness, while others might have temperature sensors or even motion detectors. Just like the motors, each sensor needs to be connected to a specific port on the microcontroller. After the motors and sensors are securely attached, it's time to power up the system. This involves connecting a power source, such as a battery, to the microcontroller. It's crucial to ensure the power source is compatible with the microcontroller. Too much power can fry the microcontroller, while too little power might not be enough to get the robot moving. Once everything is connected, we'll need to secure the microcontroller to the body of the robot. This can be done using a variety of methods depending on the design of your robot. Some might use a simple bracket, while others might require a more complex mounting system. Finally, we need to attach the robot's limbs or wheels, again depending on the design. This is usually a simple process of screwing or snapping them into place, and there you have it. We've assembled our robot piece by piece, and it's starting to look like the real deal, but we're not quite done yet. Now that our robot is assembled, it's time to bring it to life. Scene script. A robot is as smart as its programming. Let's get into that next. Now that we've assembled our robot, the next step is to breathe life into it with programming. While it may seem daunting, programming a robot is a lot like giving it a set of instructions to follow. It's about telling the robot what to do, when to do it, and how to react to different conditions. The heart of our robot's intelligence lies in its microcontroller. Think of the microcontroller as the brain of the robot. It's a small computer that we can program to control the robot's motors and sensors. To program the microcontroller, we use a programming language that it understands. There are many languages to choose from, but some of the most popular ones include Python, C++, and Java. These languages allow us to write code that can make our robot move, respond to its environment, and even make decisions based on the input it receives from its sensors. Once we've written our initial code, we upload it to the microcontroller via a USB cable. The microcontroller then runs this code, controlling the motors and sensors according to our instructions. But programming a robot isn't a one-and-done task. It's an iterative process that involves testing and debugging. Testing involves running the robot and observing its behavior. Does it move as expected? Does it react appropriately to sensor input? If not, we need to debug our code, which means finding and fixing any problems that prevent the robot from behaving as intended. Debugging can be tricky, but it's a crucial part of robot programming. It helps us refine our code and improve our robot's performance. Plus, there's nothing quite like the satisfaction of finding a pesky bug and squashing it. And remember, programming isn't just about making the robot work. It's also about making it work well. That means writing efficient code that maximizes the robot's performance and battery life. So don't be afraid to experiment and optimize. With the programming complete, our robot is almost ready to go. The final step in making a robot is testing and troubleshooting. Now that we've gathered our materials, assembled the parts, and programmed our robot, it's time to see if our efforts have paid off. Testing and troubleshooting are critical stages in the robot making process. It's where we validate our design, our assembly, and our programming. But remember, this step requires patience and persistence, as it's not always smooth sailing. Our first test is a functionality check. We're simply verifying if the robot is functioning as expected. Are the wheels turning? Is the robot responding to commands? Is the sensor picking up the data correctly? If the answer is yes, then we're on the right track. If not, we'll need to go back and recheck our work. Remember, there's no need to feel disheartened. In fact, encountering and overcoming these hiccups is part of the learning process. Next, we test the robot's performance in its intended environment. If it's a vacuum robot, we'll test it on different floor types. If it's a rover, we'll try it out on different terrains. We want to see if the robot can adapt to varying conditions and still perform its duties. Now let's say our robot is not performing as expected. This is where troubleshooting comes into play. We'll need to identify the problem, find its root cause, and then fix it. Is it a hardware issue or a software one? If it's hardware, we might need to adjust the assembly or replace a faulty component. If it's software, we might need to tweak the code. The key here is to approach troubleshooting systematically. Start by isolating the problem, then work your way towards the solution. It can be a bit like detective work, looking for clues and piecing together the puzzle. And yes, it can be challenging, but it's also incredibly rewarding when you finally solve the issue. Remember, Rome wasn't built in a day, and neither is a robot. It's a process of trial and error, of learning and improving. So keep at it, stay patient, stay persistent, and you'll get there. Congratulations, you've just built a robot. Let's take a moment to recap what we've learned today. We started our journey into the fascinating world of robotics by understanding what a robot truly is. It's not just a collection of metal and wires, but a sophisticated machine that has the ability to interact with its environment. Next, we delved into the nitty-gritty of gathering the right materials. From the simplest nuts and bolts to the most complex circuit boards, every single piece has a crucial role to play. Remember, the quality and compatibility of these materials can make or break your robot. Then we navigated through the intricate process of assembly. It's here that the robot starts to take form, piece by piece. We saw how patience, precision, and a steady hand can transform a heap of components into a working robot. We also explored the world of programming, the very soul of a robot. It's the code that gives the robot its intelligence, its ability to perform tasks, and even its personality. Finally, we discussed the importance of testing and troubleshooting. Robots like us are not perfect. They need testing, fine-tuning, and sometimes a bit of tender, loving care to function at their best. As we wrap up, we encourage you to take the leap and try building your own robot. Share your experiences, your triumphs, and even your failures. After all, every failure is a stepping stone to success. Thank you for joining us today. Remember, the world of robotics is vast and exciting, so keep exploring.